Principal axis of rotation. We have written total angular momentum of a rigid body in terms of moment of inertia tensor product with angular velocity omega. And we found that generally angular momentum will not be parallel to the angular velocity omega. The question we may ask is, can we have rotation without requiring torque? Because otherwise, since L is wobbling around angular velocity, we will require torque to support such rotation. And the answer is yes, if we spin it around so-called principal axis. For principal axis, we require that L is proportional to the angular velocity. So it's parallel to the angular velocity, which gives us an eigenvalue problem, because now we have that the tensor I times omega is the same omega times a constant lambda. In any given specific coordinate system, we will have tensor I written as a 3 by 3 matrix. And so, solving this eigenvalue problem, we will write a diagonal form of matrix I, which will have coefficients lambda 1, lambda 2, and lambda 3, where these coefficients, lambda 1, 2, and 3, give the so-called principal moments of inertia. Note that any square symmetric matrix I can be diagonalized, giving three orthogonal principal axes, new directions, x hat, y hat, and z hat. In terms of diagonalizing matrix I, we proceed in the normal way. We can rewrite our eigenproblem in the form matrix I minus lambda times unity matrix times angular velocity equals to 0. Therefore, we require that the determinant of the matrix should be 0. This gives us a cubic equation, which gives us 3 roots of lambda, as well as 3 eigenvectors, which give us directions of the principal axis. Depending on the relationship of eigenvalues, we can identify several different cases. If they're all equal, then we have a case of spherical top. If lambda 1 is equal to lambda 2, but different from lambda 3, then we have a symmetrical top. If none of the eigenvalues are the same, then we have a case of asymmetrical top. And finally, if we have one eigenvalue which is equal to 0 and the other two are equal, then we have a case known as rotor. Finally, let's consider how kinetic energy looks in terms of moment of inertia tensor. We know that kinetic energy is given by a product of generalized velocity, in our case it's omega, and generalized momentum, in our case it's angular momentum. Or we write it in terms of product of omega times moment of inertia tensor times omega. If our choice of x hat, y hat, and z hat coincides with principal axis, then we get that the kinetic energy is going to be given by the sum of diagonal terms I sub I times omega I squared. For example, if angular velocity is parallel to the z-axis, then we recover the expression we've seen already, that kinetic energy will be given by half of element of the tensor of inertia zz times omega squared.